I hope you enjoyed the video in the beginning of this lesson. This was my project over the summer. I was creating these little miniature houses, miniature homes. They are a mini size of a real version of a full house. So this was the exact one that you saw in the video, and I wanted to show you real quick how small this is, right? So this was a full-size objects shrunk down to a certain ratio so that you can have these miniature size objects, right? So these are mini scale models of a home, you know. Why do I do this? For fun, because this is what Miss Chu enjoys doing on her spare time. So this brings us to the topic at hand today. We are learning about dilation. A dilation is to shrink or enlarge an object, right? So I'm sure you heard of your pupils being dilated, and that means that your pupil got bigger than what it was before. I have to do that every single year when I go see my optometrist because I have really, really bad eyes. And so they want to make sure that everything still looks healthy. So they always have to dilate my pupil. So I know that word very, very well. It's really hard to see for the next 3 hours after they put those eye drops in you. So yeah, I got to know that very well. Anyway, so before the days of copy machines and before the days of digital things that can help us with before days of computer, this is how posters were made. People start with small scale models, scale drawings of what they want, and then they enlarge it. But unless you're a really, really great artist, it is extremely hard to make sure that the small one and the big one are really exact replicas, but just bigger, right? So this is what typically people did. Before the days of computer, they took the picture they wanted, which is this Winnie the Pooh on the side here. Sorry, I can't really turn my paper, but you can turn. In actuality, it's better to do it not turn because then you're not distracted by the fact that it has to be a Winnie the Pooh, right? So what people did was they gridded off their picture and they took it grid by grid to make it bigger. So what am I talking about? So of course, this grid right here matches this grid. And I can see in the both grids, there's nothing. So I don't want to do anything yet. Okay, this second grid matches this second grid here. So what you want to do then is to really look at what's inside the grid and see where the lines are. Again, without looking at the rest of the picture. Do not let the rest of the picture distract you, right? If I take a quick look in this picture, just this square alone, okay, it looks like this big curve, this big kind of a U is crooked and is going from one edge to the other, right? So it looks like it's going from here a little bit more than halfway, actually a lot more than halfway, and it got really close to the edge. Oh, maybe too close there, right? So let's try again. It got close to the edge, and then it's going to come back and it's going to come down. I think mine's too fat again. So again, this takes a lot of trial and error to see if you get the idea of what you want. And of course, I would recommend doing this with a pencil. And of course, through time, you want to make sure you get kind of the right idea. So I think that looks kind of like what I wanted, except maybe it's not as turned here. So again, you can tweak it and change it what you want. And I see there's a little bit of a line right there, right? So that's what you want to do. You want to take each grid and just copy what you have in the grid. All right, get rid of this check mark, right? All right, the next one, of course, and I look at the box next door. Okay, in this box, there's not a lot happening. There's a little bit of a triangle there and a tiny bit of a curve. Okay, so then I see that there's something here and there's a tiny bit of a triangle. I want to say it looks not even halfway, it looks good. And it's just a little bit of a curve. So it's just a little bit, it goes from this edge to that edge. Okay, that looks about right. Okay, so if you keep that in mind and you look at just each of the picture, you will be able to draw your Winnie the Pooh with no problem. Even if you're a terrible artist, which I know not everybody's great at this, I need to learn too. But even if you're a terrible artist, if you just look at each of the boxes and copy over what each box is, then when you're done, you should have a really nice, complete Winnie the Pooh. Hopefully now you see the picture of Winnie the Pooh being completed. You know that how to go from a small scale drawing to a large scale drawing by grading off your picture and just copying each of the grids over to create that larger picture. Now I'm going to move on to more of the geometry portion of it, right? How do we dilate this quadrilateral from the origin by a factor of 2, 3, 4, and 5? So I strongly recommend using color pencils, right? So that you can see each of the different dilations. Maybe choose one color for each of dilations. So choose a color for 2, choose a color for 3, 4, and 5. So what we're going to do is going to make this bigger. The transformations we have learned up to this point are called rigid transformations. Those are our rotations, translations, and reflection. Those are rigid transformations because the shape does not change and the size does not change. Now with dilation, the shape still doesn't change. We still have the same thing. Just like my model house here, a fridge is still a fridge, a chair is still a chair. They're still the same shape, but just got bigger or smaller. So this quadrilateral, in fact, I think it is a trapezoid because it has one pair of parallel lines. This trapezoid is still going to be a trapezoid. It's just going to be bigger or smaller than the original picture. So how do we do that? First thing you want to do is write out the coordinates of your A, B, C, D. This will make your life a little easier, so a little bit of hard work at the beginning. So find your 0, 0. It's a little harder to see, but let's see. My 0, 0 is right around here. Very good. So A looks like it's 3, 2. B looks like it's -1, 2. So -1, 2. C looks -2, -2. And D is 1, -2. Okay. I'm going to use red for my first dilation. So dilation by 2. So this is the 2. Okay. So what is it going to do? How do we dilate the object by 2? You multiply all the coordinates by 2. So A prime, B prime, C prime, and D prime. Now all needs to be multiplied by 2, which gives me 6, 4, -2, 4, -4, -4, and 2, -4. Okay, so let's draw this out. 6, 4, A prime, that's A prime, -2, 4, B prime, -4, -4, C prime, and 2, -4, D prime. Don't forget to connect your dots. Again, rulers are really helpful. The more precision you have in geometry, the better your picture is, the easier it is to understand the relationship. All right, now, first things first, you know you did it right because my shape is still the same, but got bigger. Secondly, all the lines are parallel, right? Because the same relationship should still hold. Your lines are going, I had a pair of parallel lines before, I still have one pair. But what I mean by parallel, my line AB versus A prime, B prime are parallel to each other. So the line up here, I'm going to use a different color to kind of talk to you about it. So this A prime, B prime is parallel to this AB, right? And then this line on this side is going to be parallel to the line on this side. Same thing, CD parallel to C prime, D prime, and then BC, B prime, C prime, and BC. So they're all going to be parallel to each other because it's, other than the size, the relationship is still the same everywhere else, right? The angle is going to be the same. Okay, choose a second color. I'm going to choose orange, right? So for orange, I'm going to do the scale factor of 3. What does that mean? Okay, this is A double prime, B double prime, C double prime, D double prime. It's really not true to call it A double prime, B double prime because you're starting from the original one. So yeah, I think we should still stick with the right terminology. This is a scale factor of 3. So A prime, B prime, C prime, D prime, because we're still going back to the original one. We're not going back to the red one. We're going back to the black one. So go back to the black coordinates. Now you're multiplying everybody by 3. My new coordinate now is 9, 6, -3, 6, -6, -6, and 3, -6. Okay, so again, I got 9, 6. That's A prime. I got -3, 1, 2, 3, 6. That's why I'm saying that if you have colors, I hope that this will make your life a little bit easier because there's just a lot of lines going on here. So if you have your colors, it actually makes it a little bit easier to spot what you want. All right, so that's D prime there. Okay, connect my dots, A prime, B prime, C prime, D prime, and so on and so forth. Oopsie. Okay, you could probably guess what's going to happen next with a scale factor of 4 and 5. So I'm going to speed up just a little bit to let you see what's going to happen there without wasting too much of your time. Okay. Okay, so when you are done, you should have 4 new trapezoids, all at different sizes, but they should look similar to the original one because they're still the same trapezoid tilting the same way with the same parallel lines, just bigger and bigger and bigger and bigger. Okay, all right. So let's take a quick look. This is a fun question. This is kind of like the ones where my son does in his kindergarten class, right? Which one of these don't belong? So which shape is the exception and why? So we want you to look at these 4 sailboats and tell me which one is different. Well, pause a second, think about it. And I will say that this one is different because the sail does not flip over. So the sail is not flipped over. So what's the point of this? This is to remind you that, again, in any transformation, the shape should still stay the same. No matter how we move it, no matter how we enlarge it or shrink it, no matter how we reflect it, it's still going to be the same shape. So all these sailboats are correct transformations, except the one we circle, because that one doesn't have the same thing. Nothing should happen to the shape itself except movement and enlargement or shrinkage. Okay? All right. Which figures appear to be exception? What makes a shape different than the others? What do the 3 shapes have in common? Are there commonalities in the angles? Are there differences? Are there commonalities in size? Are there differences? So there's a lot of things to talk about, right? So let's take a quick look here. I have shape A, B, C, and D. It's a little tough to see here, but I am going to say that they all look pretty good, except, pause yourself if you can't see it, but this is the one. This is different. Why is this different? Because this one has a right angle right here, whereas all the other pentagons don't have a right angle, and all the other pentagons look about the same angle, right? So this is what is really cool, right? So D has a right angle. So D is the exception, right? So this is to answer the first bullet point. What do all 3 other shapes have in common? So all others have the same angle. Right? If you take your patty paper and trace each of these shapes and just move the angles to match each other, you'll see that this angle here matches this angle here matches this angle. The corresponding angles will match. The ones in the same places will match up. So same thing. This angle here will match this angle here, will match this angle here. And you can check all the other angles as well, but you will see they're the same. So the only difference is the side. So the all side lengths are enlarged or shrunk the same way. Meaning that to go from A to C, however bigger I made one side, I'm gonna make all the other sides the same size bigger. So if it's 3 times bigger, all the other sides are 3 times bigger. If it's smaller, all the other sides are 3 times smaller, right? So it's enlarged and shrunken by the same way. Okay, same thing here. Let's see. Part B, same idea. Which of these triangles, which one doesn't match? Well, I'm going to say that is triangle C. Why? Because I can see that in angle A, there's a really nice big obtuse angle there. It's the same angle as angle D here, and the same angle here in triangle B. The only one that doesn't have that giant obtuse angle is this angle C. It has an obtuse angle, but it's not as extended and not as big. So that one has a different angle, okay? So I would say C has a different angle. All right, same answer as before. All others have the same angle. And then what the difference is, all the sides are enlarged or shrunken the same way. So all the sides are enlarged or shrunk the same way. Okay, I hope you have fun with dilations today.